Hi Year 12s. Welcome to a short video on sketching quadratic graphs. I apologize for not being there in person today as I am attending the physics teachers conference. You have spent at least a year, possibly more, working with quadratic graphs. It's not possible to cover everything that you've learned in that time. I want to spend most of our time in this video on the most difficult aspects of quadratics, which are completing the square, using the quadratic formula, and using the discriminant. So today's video will focus mainly on the algebra, but your work program also requires you to sketch graphs as well. So I'm assuming that you know how to do that. Um, if you need help, just refer to the textbook or contact me over the weekend. So let's get into it. Here's a quadratic graph, and I want to just briefly point out some key features that you should be aware of. So first, we have the y-intercept. This is the point where the graph intersects the y-axis or the vertical axis. Similarly, we have the x-intercept or the x-intercepts, depending on where the graph is positioned, and this is where the graph intersects the x-axis or the horizontal axis. We have the turning point, which is going to be a local minimum or a local maximum on the graph. And finally, we have the axis of symmetry. This is where the graph is a mirror image of itself about some vertical line. One thing that I should say is that a graph might not have any x-intercepts if the turning point is above or below the x-axis and the scale factor a matches the sign of the y-intercept. So for example, I could have a graph like this, a positive parabola with a turning point above the x-axis, or I could have a parabola below the x-axis, which is negative. So you're always going to have a y-intercept, but you might not have any x-intercepts. So just be aware of that. All right, so we've got a qualitative picture of what a parabola looks like and the features. But now we want to describe these using an equation. And you've met three different kinds of equations to describe quadratic graphs. The first one is polynomial form, ax squared plus bx plus c. It's the one that everyone meets for the first time, and it's the least useful one. Because by looking at this equation, I can only read off one useful piece of information, and that's the y-intercept, c. I can't tell what the turning point is, and I can't tell what the intercepts are. In order to get that information, I will need to do some algebra to change the equation from polynomial form to one of these other two forms. Turning point form, as the name suggests, gives us the turning point. So if I can write the equation in the form y equals a bracket x minus h bracket squared plus k, then I automatically know that the turning point is at hk. You should recognize this as a transformation, h units to the right and k units up from the origin, with a dilation by a factor of a before those translations have occurred. Since the turning point occurs on the axis of symmetry, we could describe the axis of symmetry with the equation x equals h. Remember, x equals some number defines a vertical line rather than a horizontal line. Turning point form is good because it gives us the turning point, and that's a very useful piece of information, but it doesn't give us the x-intercepts. At this point, you might choose to solve the equation y equals 0, and it'll be quite straightforward. You'll just need to move k to the other side and take square roots. But sometimes there's an even easier way to do it, and you can read it off a factorized form of the quadratic equation. So if I can write it in this form, a times x minus p times x minus q, then I automatically know the x-intercepts are at p and q. Furthermore, because I know that the parabola is symmetric, if the graph passes through two x-intercepts, the axis of symmetry has to be halfway between those intercepts. So I could write this as x equals p plus q divided by 2, halfway between the intercepts or the average of those intercepts. Part of your work in dealing with quadratic equations is learning to recognize which form is useful given the type of question that's been presented to you. And that's only going to come with experience. So now I think there's another question that's worth asking. Okay, so if I have these three different forms, how do I change from one form to another? Well, to go from polynomial form to turning point form, we have to use a pretty algebra heavy method called completing the square. If I want to go from polynomial form to factor form, I need to do something called factorizing. And one thing that we should note is that it's not always possible to factorize. So I'm always going to have a polynomial form and a turning point form, but I might not necessarily have a factor form. This is when the graphs look like the ones I drew previously. So it's not always possible to factorize over the real numbers. If I want to go backwards, well, I just need to expand the brackets. And if I want to go from turning point form to factor form, it's factorizing as well. You'll need to use something called a difference of perfect squares. I'll talk about this in another lesson in the future. Going backwards from factor form to turning point form, it's probably easy to go through polynomial form and then to turning point form, because you still got to complete the square usually. Completing the square is probably the most difficult part of this exercise, so I've developed two examples to illustrate that, which we will do now. So here's our first example. I'm giving you the quadratic equation y equals x squared plus 10x plus 16, and we're asked to find the turning point. Um, Now, even though I'm going to demonstrate completing the square, if I can avoid the hard work of completing the square, I'd like to use an easier method if possible. So one thing I'm noticing immediately is that I can factorize this quadratic as x plus 2, x plus 8. If you're rusty in factorizing, please speak to me immediately. Send me an email. Just remember that our goal is to find two numbers which add up to 10 and multiply to 16, and those numbers are 2 and 8. So this means the graph passes through -2 and -8. The axis of symmetry is going to be the average of -2 and -8, which is -5. So when x equals 5, sorry, -5, y equals -5 all squared plus 10 times -5 plus 16. So that's -25 plus 16, which is -9. So the turning point is -5, -9. Notice I did not need to complete the square because I could find an easy way of factorizing this quadratic. That's not always going to be possible. So if it wasn't possible, this is what we would need to do. To complete the square, what I need to do is take half of the coefficient of x and square it. So in this case, half of 10 is 5, but I'm going to deliberately write 10 on 2 to make it clear. So plus 10 on 2 squared, take 10 on 2 squared, plus 16. You might be asking, why did you plus and minus it? Well, if I plus something, I've changed the equation. But if I plus and minus the same number, they cancel out. So I claim that by inserting these two terms, plus 5 squared and minus 5 squared in the same line, I have the same equation as I did previously. Okay, so I'll leave that highlighted so that it's clear. So we continue. X squared plus 10x plus 5 squared minus 5 squared plus 16. X squared plus 10x plus 25 minus 25 plus 16. And what you should notice is this first part has now become a perfect square. That was why we needed to divide by 2 before squaring that term and adding and subtracting it. So this gives us x plus 5 all squared minus 9. And since the turning point occurs at hk, when I write my quadratic in the form a bracket x minus h squared plus k, I get a turning point at hk. So once again, the turning point is at -5, -9. If you can avoid completing the square, I would advise doing that. Like, avoid it, because it's very easy to make a mistake. One other thing I want to say is if ax squared plus bx plus c equals 0, the axis of symmetry is x equals -b on 2a. You can just use that as a result. So for example, if I use that formula here, I'll have b equals 10 and a equals 1. -10 divided by 2 gives me -5. So I could have used this for method 1 as well, as an alternative. So we could have factorized, we could have used -b on 2a, or we could have completed the square. 3 different methods for solving the same question to find the turning points. And unfortunately, I can't tell you which one you should use because it'll depend on the question that's being asked. With more experience, you will be able to make a better judgment of which one's going to be the easiest. The general advice I would give is avoid completing the square if possible. All right, another example. This one I have purposely set up so that you can't factorize it. So we only have 2 approaches this time, -b on 2a or completing the square. So this time I'm going to demonstrate the -b on 2a method. So b is -6, so -b is +6, and 6 divided by 6 is 1. When x equals 6, well, when x equals 1, I should say, y equals 3 times 1 squared minus 6 times 1 plus 10. 3 minus 6 plus 10, which is -7. So the turning point is at 1, -7. Look at how easy that was. If we didn't know that the axis of symmetry was at -b on 2a, this would be a very difficult question and we would have to complete the square. However, completing the square is a skill that is assumed in the methods study design, so I want to teach it to you and make sure you know it. Our first step is to take out the factor of 3, which is the coefficient of x squared, like so. Now what I will do is I will take half of the coefficient of x inside the brackets, square it, and then add and subtract that. Here, the coefficient is -2. If I add something, I have to subtract it so that the equation stays unchanged. I'll color code it for you to make it really clear what we're doing. So I haven't changed anything because all I've done is I've added 0 essentially. So 3x squared minus 2x plus -1 squared minus -1 squared plus 10 on 3. So 3x squared minus 2x plus 1 minus 1 minus 10 on 3 plus 10 on 3. All right, the perfect square is going to appear in the first 3 terms there, which I have surrounded in the purple bracket. So it's going to be 3 big bracket x minus 1 all squared. Now, -1 plus 10 on 3 is 7 on 3. And now, if I expand the big bracket, I get 3 x minus 1 squared. This should be 7, not -7. Apologies. That makes more sense. So 3 bracket x minus 1 squared plus 7. There we go. All right, so we get the same answer. Turning points at 1, 7. I think it's really clear which one is easier. So if you can avoid completing the square, do so. I'm happy for you to use -b on 2a, but if you can factorize first before finding the average of the two x-intercepts, I would advise doing that as well. Okay, I've got one more example and then we'll leave it at that. So I want to quickly recap the quadratic formula. If I give you a quadratic equation, ax squared plus bx plus c equals 0, and here we've got to assume that a is non-zero, otherwise it's not truly a quadratic equation. And then you get this really nice formula, x equals -b plus or minus the square root of b squared minus 4ac on 2a. This is not given on the formula sheet at the end of the year. So when you take exam 1 with no notes and no calculator, you will need to have this memorized. If you don't have it memorized, practice it enough times until you do have it memorized. Now, closely related to the quadratic formula is this thing called the discriminant. The discriminant is defined by b squared minus 4ac. Again, we are assuming that we're dealing with a real quadratic, so a is non-zero. And you should recognize the discriminant as appearing underneath the square root term of the quadratic formula. Now, why is this interesting? Why is this useful? The discriminant tells us how many solutions there are to a quadratic equation. Without having to find them. So for example, those solutions could be very complicated, involving scary square roots and fractions. And perhaps I want to sketch a quadratic graph, and part of sketching a graph involves finding the x-intercepts, so I might be interested in whether my graph hits the x-axis. I can do a very quick calculation involving the discriminant, which will tell me how many x-intercepts there are. So you should recall from your Year 11 studies, if the discriminant is positive, there are two solutions. If the discriminant is 0, there is only one solution. And if it's negative, there are no real solutions. So with that in mind, let's do our final example. Here is an equation, kx squared plus x minus k, and I've set that equal to 0. This isn't just one equation, it's a whole family of equations with this parameter k, and because you're in year 12, you're expected to be able to deal with families or parameters of curves all at once and analyze them algebraically like this. So the claim is, no matter which value of k I choose, so k could be any real number, there's always going to be two real solutions. How would we go about showing something like this? And the answer involves using the discriminant. So the symbol for the discriminant is the capital Greek letter delta, which is the triangle, which is b squared minus 4ac. The coefficient of x is 1. The coefficient of x squared is k. And the constant term is negative k. All right. So if I simplify this expression, I find that the discriminant is 1 plus 4k squared. And this is where we need some insight. In order to show that there's always two real solutions, we need to show that the discriminant is always positive. So now we need to make a connection. How do we know that 1 plus 4k squared is positive? Well, since k squared is non-negative, that is, it's greater than or equal to 0, for all real numbers k, 1 plus 4k squared is greater than or equal to 1. So the discriminant is greater than or equal to 1, or the discriminant is positive for all k. See how I've reasoned? I haven't just calculated the discriminant. I've explained here that it's always positive. So since the discriminant is always positive, there will be two real solutions. This is the level of reasoning you would be expected to demonstrate in exam 1. So with no notes and no calculator. You'll notice towards the end of the exercise there are lots of questions on the discriminant. If you need more practice, feel free to do more than what I've assigned from the work program. I haven't released the work program yet, so I'm just going to tell you which questions I would like you to do from this exercise. There are quite a few, and I know that you have a lot of homework in other subjects, but quadratics are a very foundational topic, and you need to be able to factorize, use the quadratic formula, sketch graphs, and use the discriminant, and perhaps even complete the square. So I am assigning quite a few questions, and I would like you to try to have these all finished by class next Monday. If you need help, please remember that help is available by sending me a message on Compass or on Teams, and I also expect that you are reading the textbook to fill in any gaps that you might have in your knowledge. So the worked examples are there as well, but if you need help, please do reach out. All right, thanks for watching, and I look forward to seeing you on Monday.